It's one of the cornerstones of modern physics. Its implications are so profound they can make your head spin. And it may just be one of the greatest intellectual achievements in human history. What is the theory of relativity? Well, actually, there are two related theories, special relativity and general relativity, that together revolutionized our understanding of the universe. First up, let's talk about special relativity. So Albert Einstein published his theory of special relativity in 19... And he did this at a time when physicists had developed the laws of motion for objects at rest and in motion. But there was a problem. You see, scientists had also discovered that light travels at a constant speed, and they couldn't reconcile this fact with how velocities are normally calculated. Let me explain. According to the laws of classical mechanics, velocities add together. For example, if you throw a ball toward the front of a train that's moving forward, then the velocity of the ball, as seen by someone standing next to the tracks, would be the sum of two velocities, the velocity of the train and the velocity of the ball relative to the train. But here's the twist. Scientists knew that the speed of light does unchanged no matter how fast the source of the light is moving. Suppose you fire a laser beam forward while riding on a rocket traveling at half the speed of light. According to classical mechanics, the light should be traveling at 1.5 times the speed of light, which doesn't make sense. This apparent contradiction between the known constant speed of light and the rules of classical mechanics was a major puzzle in physics. Einstein cracked this case wide open with his theory of special relativity, which was based on two postulates, which are basically strong assumptions or ideas that you start with before you build the theory. Einstein's first postulate was the principle of relativity. It states that the laws of physics are the same for all observers who are not accelerating. Now what does that mean? Well, imagine you're inside a box, on a smooth, level surface, floating in deep space far from any other objects. There is no way for you to tell whether you're at rest or moving at a steady speed in a straight line. If you roll a ball across the floor of the box, it will move in a straight line just as it would on Earth. In other words, the laws of physics work the same whether you're still or moving at a steady speed. In such cases, these observers are said to be in inertial reference frames. Einstein's second postulate was even bolder. He stated that the speed of light in a vacuum is the same for all observers regardless of the motion of the light source. For example, if I were to fire a laser beam towards you, when my spaceship is at rest, and then again, when it's zooming away from you at half the speed of light, the beam would be traveling at the same speed in both cases. These two postulates might seem straightforward, but they turned out to have some crazy mind-bending consequences. Let's look at 5 of them. Number 1. Time dilation. Imagine you have a friend who is an astronaut living on a spaceship that is zooming away from Earth at a very high speed. Time would pass more slowly for your friend than for you on Earth. That means time would be passing differently for the two of you. Wait, it gets weirder. It's not just because you're observing your friend from Earth. Even if you were on the spaceship with your friend, time would still pass slower for you both compared to someone on Earth. Does that make sense? Well, let's think about why this happens. Consider the following scenario. You are standing next to a spaceship watching your friend on board the ship flash a strobe light back and forth, because your friend is moving away from you at a high speed. Each flash of light will appear less frequent to you than it would if the ship were at rest. From your perspective, the flashes of light seem to be spaced farther apart, and this makes it appear as if time is slowing down for your friend on the spaceship. This phenomenon is known as time dilation, which is a consequence of the fact that the passage of time depends on your frame of reference. But why does this happen? Well, to understand this, let's look at a bit of math. The proper time interval between two events is the shortest amount of time between those two events. It's measured along a path that connects those two events. And this path is usually represented as a straight line on a graph of spacetime. Now, if you want to calculate the time interval between two events for someone who is in a different frame of reference, then you need to use a longer path which accounts for the relative motion between the two observers. This longer path is not a straight line, and because of this, the time interval measured along this path is always greater than the proper time interval. That means time appears to be passing more slowly for the observer who is in relative motion compared to the observer who is at rest. The faster the relative motion, the more pronounced this effect becomes. And as an object approaches the speed of light, this effect becomes infinitely exaggerated, and time effectively stops for that object. Number 2. Length contraction. Let's say you're standing on the platform waving goodbye to your friend who is on a spaceship that is speeding away from you. From your point of view, the spaceship appears to be moving away from you at a very high speed. Now let's imagine that on the spaceship, there's a rod whose length you know exactly when the spaceship is at rest. When the spaceship is zooming away from you at a high speed, the length of that rod appears shorter to you than it would if the spaceship were at rest. This phenomenon is known as length contraction. To quantify this, let's consider a spaceship that is moving at a speed of 0.8 c, about 80% the speed of light. Relative to an observer, The observer measures the length of the spaceship to be 50 meters long. What would be the length of the spaceship as measured by an observer who is on the spaceship? Well, you can use the following formula to calculate this. The length observed by the stationary observer is equal to the length observed by the moving observer multiplied by the square root of 1 minus the ratio of the speed of the spaceship squared to the speed of light squared. No. 3. Relativity of simultaneity. Imagine you are standing on a train platform watching two lightning bolts strike the ends of a train that is passing by. You observe the lightning bolts striking at the same time. However, a person sitting on the train would see the front lightning strike before the rear lightning strike. This is because the passage of time depends on your frame of reference, which means that what happens simultaneously for one observer may not be simultaneous for another observer in relative motion. No. For mass-energy equivalence, perhaps the most famous equation in the world arises from the theory of special relativity. E equals mc squared, where E represents energy, m represents mass, and c represents the speed of light. This equation shows that mass and energy are equivalent and interchangeable. This means a small amount of mass contains a huge amount of energy, because the speed of light squared is a very big number. This equation explains how stars generate energy by converting a small amount of their mass into a tremendous amount of energy. Nuclear bombs also harness this principle, releasing the energy stored in the bonds between atomic nuclei. Finally, no. 5. Spacetime. One of the most significant contributions of special relativity is the idea that space and time are intertwined in a four-dimensional fabric called spacetime. In the old Newtonian view, space and time were separate and absolute. That meant no matter where you were in the universe, you would agree on the same time. However, Einstein showed that time is relative, depending on your frame of reference. This realization led to the concept of spacetime, a unified four-dimensional continuum that incorporates both space and time. Spacetime allows us to keep track of events in the universe by assigning them coordinates similar to how we use x, y, and z coordinates to pinpoint locations on a map. However, in spacetime, instead of using 3 dimensions, we use 4 dimensions, 3 spatial dimensions, x, y, and z, and 1 temporal dimension, t. This means an event in the universe can be identified by a unique set of coordinates, like the famous coordinates for the Big Bang, which is 0, 0, 0, 0. So those are 5 key ideas from the theory of special relativity. Now that we've covered special relativity, let's move on to Einstein's theory of general relativity. This theory extends special relativity to include acceleration and gravity. It introduces a revolutionary idea. Gravity is not a force, but a curvature of spacetime caused by mass and energy. To fully grasp this idea, it helps to understand a few key points. First, according to special relativity, only observers in inertial frames of reference, that is, observers who are not accelerating, can have their motion described by the simple equations of special relativity. However, in everyday life, we experience acceleration all the time, whether it's when we walk, drive, or fly. General relativity deals with situations involving acceleration. Second, in special relativity, the laws of physics are the same in all inertial frames of reference. But in general relativity, Einstein took this one step further. He postulated that the laws of physics are the same in all reference frames, including those involving acceleration. Finally, in special relativity, the background of space and time is assumed to be flat and unchanging. However, in general relativity, space and time are allowed to curve and change in response to the presence of mass and energy. So let's put these ideas together. Imagine you're standing on the surface of the Earth. You feel a downward pull, which you experience as gravity. According to Newtonian physics, this happens because the Earth exerts a force on you. But Einstein turned this around. He proposed that the Earth warps or curves the fabric of spacetime around it. Here's an analogy. Picture a bowling ball placed on a stretched-out rubber sheet. The ball causes the sheet to sag or curve inward. Similarly, massive objects like the Earth warp spacetime. This curvature of spacetime determines how objects move in the vicinity of the Earth. An apple, for instance, doesn't fall to the ground because the Earth pulls it. Instead, it falls because it's following the curved path in spacetime created by the Earth's mass. This curved path is called a geodesic. General relativity made several predictions that were later confirmed by observations, lending strong support to Einstein's theory. First, it explained the slight discrepancies in Mercury's orbit that Newtonian gravity couldn't account for. Next, it predicted that light would bend around massive objects, which was confirmed during a solar eclipse in 1919. Third, it predicted a type of gravitational lensing where the gravity of a massive object distorts and magnifies the light from objects behind it, creating multiple images or rings around the massive object. Fourth, it predicts that clocks run slower in stronger gravitational fields, which is now taken into account in GPS technology. Fifth, it predicts that light loses energy as it climbs out of a gravitational field, stretching its wavelength towards the red end of the spectrum, a phenomenon known as gravitational redshift. And finally, it predicts the existence of gravitational waves, ripples in the fabric of spacetime caused by accelerating massive objects. These waves were directly detected in 2015 by LIGO, providing strong evidence for general relativity. So there you have it, a whirlwind tour of Einstein's theories of special and general relativity. These theories revolutionized our understanding of the universe and continue to be cornerstones of modern physics. Thanks for watching. If you liked this video, check out other videos on great scientific theories, such as quantum mechanics or the theory of evolution.